In this video, I want to show you how you go about programming the program. So um, the first thing you would do is inside of RAWs. This is where you would create a file that will have the machine code that we'll use within Vivado. So, this is the example assembly code from the last video. And, once you have it saved, here, I'll go save it here. You go ahead and assemble it. And I didn't point this out in the last video, but right to the left of this column that is titled Basic, and this is where the assembly language instructions are. Well, right to the left of it, in this column where it says code, this is the machine code for the corresponding assembly language instruction. And you can also see it shows the address where the instruction is located. So part of the assignment for hardware 1 is being able to translate between the machine code and the assembly language instruction, and that information is found in the assembler manual. The RISC-V Otter assembler manual has that information. Okay, but as far as getting this program into the program, what you would do is a memory dump, which is this button right here, or you can just go to dump memory right here. Either way will work. I'll use the button. Okay, and this menu comes up, and all you have here is a text segment, which is the code. But we need to put it into a hexadecimal text format. Okay, so you want to choose that. And then you just choose dump the file. And let's see, I already have done this. So the suffix that you want to use is the .mem. And you can see here that I called mine otter_mem.mem. And you can call it whatever you want, but it does have to match what you have in the vivado file that Dr. Hummel created that I'll show you in just a moment. Okay, so I've already created this, but again, you would just put the file name and save it. Alright, so that's all there is to getting that mem file. Now in Vivado, you would go ahead and add that mem file just like you do other source files. So just like you add a design source file or a sim source file, you would choose this add source, and you want to add a design source, and you would just go to where that mem file is located, and you would just go ahead and add it. So it's no different than adding other files when you add that mem file to Vivado. And as you can see, Vivado will list it as a mem file. Now, the program, the Verilog or system Verilog code for the program, that is given. Okay, this is code that Dr. Hummel wrote, and what this does is produce a memory inside the FPGA. So I'll just point out a few things here. This part of the code right here, that's what's creating the memory, and specifically this code here will create 16K registers that are 32-bit. And for 16K registers you need 14 addresses. And then this initial segment here, what this is doing is it's taking the machine code that's in that mem file that you created in RARs, and it's putting it into the memory. Okay, so that's what this line of code does. Now, one thing to be certain about is, this name here in the code has to match what you call the file. I actually made that mistake initially, where I think in Dr. Hummel's code this is actually otter_memory.mem. But as you saw in RAWs, I named it otter_mem.mem, so I had to change this to make it match. Okay, if these don't match, then your simulation isn't going to work. You'll just get like an undefined output if you have the wrong file name here. Okay, and then this last bit of code is what's taking the data at each of the addresses of the program and then putting it at the output, which is named instruct. Okay, so again, this code here you just take as is. It's given to you. Again, you might have to change this file name depending on what you name your file, but other than that, you don't have to make, there's no reason to change anything. It's all ready to go. But you do have to create a sim file or a test bench. This is the test bench that I have. Depending on your CP133 instructor, you might do things a little bit differently, but you can see here, I like to call my sim file the same as what I called my design source, but I just add sim to the end. Okay, and then I just have the inputs and the outputs for the sim file here. The next line, UUT stands for unit under test. And you can see I'm just connecting the inputs and outputs of my source file to the inputs and outputs of my sim file. Go back and check here real quick. So you see, I have inputs clock, prog, address, and instruct. And that's what I'm using here. But then for my sim inputs, outputs, I have clock, address, and IR. So this is just connecting the unit under test to the test bench, okay, the sim module. And then this part of the code is just creating the clock with a period of 20 nanoseconds. Here, this is just going to increment through the addresses by 4, because remember, each instruction is delineated by 4 in address, right? Because each instruction is 32 bits, okay, and 32 bits is 4 bytes. And then the program is byte addressable, so each byte has an address, right? So your first machine code instruction that's located at address 0, well, it actually takes up 4 addresses, right? Because there's 4 bytes. So the least significant byte will have address 0, then the next byte will have address 1, the next byte of that instruction will be address 3, and then the most significant byte of that address will be address 3, right? So that first instruction takes up byte addresses 0 through 3. So that means your next instruction starts at address 4, and it contains byte addresses 4, 5, 6, 7. So then the third instruction would start at address 8, right? 8, 9, 10, 11. The fourth instruction starts at address 12, okay, and so on. And of course, this is all in hex. So, like address 12 would be address C, right? Because C is 12 in hex. All right, so that's why this part of the code, that's why we're incrementing the address by 4, because that's where each instruction is. Like every 4th address is an instruction, starting at 0. And then this here, this part of the code just initializes the clock and the address to 0. So if you have a successful simulation, it should look like what I have here, where for each pulse, right, after the positive edge of the clock pulse, you should have the corresponding machine code for that instruction. So you can see here, after the first clock edge for the clock, we have this machine code here at the output IR, so that should match, and it does. Okay, see, it's right there. It matches what I have in my mem file. And after the second clock edge here at address 4, you can see this 014000513 in hex. That's the machine code of the instruction located to that address, and it matches. Okay, so that's really what hardware 2 is all about. It's just showing that each assembly language instruction has a corresponding machine code. It's the actual machine code that gets loaded into the program, and then it's just using vivado, with this Verilog code that represents or models the hardware portion of the memory that is the program. Again, Dr. Hummel created this, and this is what you should use. Okay, we don't expect you to do this on your own. But then it's just setting up vivado and just making sure that you can load it and verifying with the simulation that indeed it gets loaded correctly.